Okay, looks like question 41, talking about half-lives. Half-life is pretty interesting concept because no matter where you start and where you end in time, once a half-life passes, half the material has been decayed. So, and half-life is different for every isotope. So it's kind of tricky concept to get your head around. So first of all, let's look at the first part of the question where it says the hottest and it's most stable. So the hottest right here will be the one that decays the fastest, and the shortest lifespan right here is when we have Krypton 73 with a half-life of 23 seconds, which means it's decaying pretty fast. Krypton 81 right here will be the slowest or most stable. As its half-life looks like this: 2, 1, 2, 3, 4, 5. I'll move it over. Basically, its half-life looks like this. Sorry. 1, 2, 3, 4, 5. So it's going to decay in half every 210,000 years. So basically, it's not doing anything. It's like watching grass grow or paint dry. So that's the most stable one right here. But this one decays in half every 27 seconds. So it's going to be the hottest. So this hottest will be right here. And the most stable will be the one that doesn't do nothing over 200,000 years. Looks like it's pretty stable with me, doing nothing, like watching the grass grow. Now, what I want to focus on, first of all, in terms of the question here, talking about the UG is micrograms. I'm not even worrying about the grams or the unit right now. I'm looking at 125 micrograms. I'm going to use this example right here for Krypton 76 because the reason why I'm using it is because the units match up with the units here. So when you do the calculation I'm about to show you, make sure the units are all the same as the half-life. So I'm going to try this one here. Before I do it for real, I'm going to take a common sense approach to it to help you understand what is exactly going on with this type of question. And by saying that, I mean it looks like this. Alright, so I'm going to go back for a second. I think it says 125. Yeah. So here, this graph, it shows what's happening in terms of half-lives. So what I'm going to point out here is this piece right here. We start out at 200, for example. At T1, or 1 half-life, we have, of course, consider this to be quantity. We had 200 and 1 half-life. We're going to have 1 half gone, 1 half remaining. So it's now 200 is down to 100, 1 half-life. Now the thing about this is, after a second half-life, it's kind of like starting over again. You go from 100 to half of 100, which really now is now down to 50. So in 2 half-lives, we've actually gone down to 150, which basically what happens, it creates a curve that looks like this. This is called the logarithmic curve. Now log, I'm going to keep the math pretty basic. I'm not sure what your skills are in math. So most people I deal with really hate math. So I'm going to keep it pretty basic. Most logs, when it looks like this, basically are in terms of what's called base 10. But this curve here is called a natural log, or log to the base e, which I would say log to the base e instead of 10. And that's referred to as a natural log, or sometimes you might hear it say referred to as long. So that's how it decays in a curved fashion, because what happens, the less we get, it starts with, sorry, as it decays in half, even though it gets less and less and less, it still decays by half every time. So it results in a curve that looks like this. That's the easiest way to say it. I can get more detail, but we'll see how it goes. If you have any more questions, just send me another note and I'll get more detailed. I'm trying to keep it simple right now. So let's look at the example here. I want to use the one I just said a minute ago. Where we have, this is going to be just a basic example of what's happening. And then I'll show you the real function to get the real answer. But I want to illustrate the concept of what's happening before I do that. Because once you get the concept down, everything else kind of makes sense. So if I'm starting out with 125, 125. Doesn't even matter units. 125. And my half-life is, I think it says 14.8. Yeah. 14.8 hours. So the question is, how much is remaining in 24 hours? I think that's what it says. Double check. How much is that remaining after 24 hours? Okay, great. So, first thing we need to know or realize, that, and this is an approximation because I'm going to use, what I'm going to show you right now first of all, just to get your head around it. Basically, it would be a straight line. I would draw it this way. But this is to help illustrate the concept I'm trying to show you. So, first thing we need to do is determine how many half-lives, based on 14, how many half-lives are in 24 hours. Well, take 24, divide it by 14.8 hours. This is where the units cancel out. You notice they cancel because hours cancel. And this is a pretty basic function, but I'm just using it to illustrate a point. Then if we use a calculator, and it looks like this. Basically, it looks like we're going to take this, turn it on. 24 divided by 14.8. Oops, my bad. 8. That turns into 1.62, just rounding up to two different places. 1.62. Now, if I were to break that down into simpler terms, what that really means is that I have one half-life, and I have 0.62 of a half-life. So you're thinking, what? What's that got to do with anything? Well, let's go back to the numbers up here. The number up here says we're starting out with 125. Oops, my bad. 125 as our starting value. So just take the number right there for first of all, just to get started. So after one half-life, we have 125. 125. This is just to show you the concept first. 125 after one half-life. We're going to have, you got it, half that much left. So 125, oops, 125 divided by 2, which means after one half-life, we're going to have left 62.5 micrograms. But that's just one half-life. Now we have 0.62 half-lives. So what we have left to worry about is 0.62 half-lives. So 0.62 breaks down into 0.5 half-life, or 1/2 a half-life, and 0.12 of a half-life. So starting with 62.5, right here, if we took this as our starting value now, half of a half-life of that would end up to be, you got it again, 60, back to my other color. Sorry, I'm pretty picky on colors. We have 62.5. 62.5. If we had one more half-life, we would divide that by 2. So it would look like this. Divided by 2. We would lose, this work is kind of complicated, we would lose 31, or have 31 grams or micrograms remaining, 31.3 say. But the thing is here, what I'm trying to show you now is that this is not, this will be after an entire half-life. So we don't completely lose 31.3. We only lose half of that value, because it's just 1/2 of a half-life. It gets easier when I just show some math behind it, trust me. But I'm just trying to show you how the half-life works. Hopefully I'm not confusing you more than you probably already are. So now if I had 31.3, so 31.3 divide that by 2 equals, now for half of that will be 15.7. So then for 1.5 lives, 1.5 half-lives, this is confusing, it's going to look like 62.5, the previous half-life, minus 15.7, which now looks like 62.5 minus 15.7. Oh, now we're down to 46.8. So you see how it's decreasing. It's decreasing by half-lives. So the first one we did here, I'll just go back and just recap for 1 second quickly. First time we did 1/2 life was 1/2 the original value. Pretty easy. First value was here. Oops, my bad. I don't know why it's doing that. First value was here. So the first half-life was 1/2 of that. The second half-life wasn't a half-life, it was half of a, I don't know why it's doing that, sometimes it does these things. The next piece was 1/2 a half-life, which instead of a full half-life being 31, 1/2 of a half-life was 15. Now you see the value is getting pretty close to 40. Okay? Reason why it's not going to be exact is because of this wonderful, lovely curve function right here. If it was a straight line, these numbers I'll be showing you will be exact. So to get past this curve function, we have to use the logarithmic scale. Yay, so much fun. New page. Using the logarithmic scale looks like this. So we have natural log, may have seen this or maybe not, is going to be equal to n over the initial n, which means it's going to be the days, or hours in our case, over half-life. So this equation gets a little more complicated because now I'm not going to get into a big math conversation. If you want to see the math conversation, I'll explain the whole math thing. But trying to keep it simple, it looks like this. The real equation breaks down into negative natural log 2 multiplied by t over t 1/2, which is referred to as the half-life. Now, this is what I'm trying to hopefully make it common sense first, math second. So now what's going to happen in our case, it's going to look like this. We're going to have natural log of 2. Natural log of 2, we'll show my calculator right here. The natural log of 2 will be, the natural log will be the ln. Oops, my calculator goes backwards. So I have to put the ln and the 2. Oops, my bad. Brackets, I'm going to put in there. Which looks like this. And because it's negative, it's going to make the whole thing negative. So it's going to be negative 0.693. That's going to be multiplied by, in our case, back in the question here, looks like 24 hours and 14.8. So we're going to have 24 on the top. 14.8 on the bottom. The reason why units have to be the same, of course, is because they cancel out. Dimensional analysis. And then in our calculator, we can just do this. Because it's all multiply and divide, we can just go simply straight into it. I'm just going to go back this way. Say multiply by. Actually, never mind. I'm going to put 0.6. Oops, my bad. Do a negative first. Negative 0.693 multiplied by 24 divided by 14.8. That's going to give us. Only back to blue color. Negative 1.12. Now, that's in logarithmic scale. To get it back to a number that makes sense to us, we have to take the antilog. On my calculator, it's done by second function, or sometimes referred to as inverse. Inverse ln, and sometimes in calculators it just simply shows up as e to the x. So it looks like this in my calculator, some like this, or some simply e to the x. So when I do that, then when I end up with the number that looks like this, it's going to look like antilog, or in other words, inverse log. Again, I'm not sure your math skills, but I would write it as log minus 1 of negative 1.12, and taking the inverse log of that, looks like this. Line second function, inverse log. Oh, sorry, I'm going to put the number in here. 1.12. Close that. And you see we get 0.326. Well, that translates into 32.6% of the sample remaining after the time. Now, if we did our calculations correct, based on what we've done before, we should be getting somewhere around 40. Right? So, if I take 125, my original number, 125 micrograms, multiplied by 32.6%, we will get a number that looks like and we get 40.8 micrograms, which kind of makes sense based on our common sense approach. The common sense approach didn't work right because the common sense approach was a straight line, the logarithmic function is not. So the correct answer is right here. Because of the curve in logarithmic scale. The other questions work exactly the same way. Just be very careful with the units. If you're talking in seconds, make sure everything's in seconds. If you're talking in days or years, make sure everything's converted to days or years. All the units are the same, and they should work out fine. Have fun. Chemistry is a blast. Good luck. Bye.